as we have discussed in the last class, we discussed random walk, symmetric random walk, and how we can scale it slightly up and down, and so that we can make it more looking more zigzag and go towards what is called a Brownian motion. So, the Brownian motion is a continuous stochastic process which exhibits the property of a symmetric random walk. So, that is the idea of a Brownian motion. So, for example, if you look at the motion of a pollen grain in water, it would be something like this. More zigzagging than this, then I can draw. So, this is something motion of a particle in a gas chamber, a motion of a molecule. So, Brownian motion encapsulates lot of phenomenon. So, what did I say? The best way to remember of Brownian motion is that Brownian motion is a continuous analog of symmetric random walk. It is in the continuous setting, it behaves in the way a symmetric random walk behaves in the discrete setting. So, as usual, I will have the probability space which is written down here. So, Brownian motion, so your stochastic process Wt, some people write W lower index t, it is up to you, it does not matter, Wt is called a Brownian motion if given any time points, t is time actually, so writing time points, say Tm, Tn, whatever, does not matter. Even any time points like this, the increments are independent. The increments means just like the way you have done increments in the symmetric random walk, the increments Wt1 minus Wt0, Wt0 is actually 0, W0 is 0. Just a minute, I think I should just change it a bit. A stochastic process with W0 is equal to 0. So, it does not matter, whatever be your scenario omega, W0 is always 0. So, it is identically a 0 function. So, W0 itself is a function, please remember it is a random variable. So, whatever be the form of the random, whatever be this random variable, whatever be the scenario omega, W of that would always be 0. That is the meaning of the whole thing. So, this Wt2 minus Wt1, these random variables, these increments in the random variables means how much change you are having, basically you are telling that how much zigzagging has taken place in the interval T2 to T1, T1 to T0 to T1, T1 to T2, T2 to T3 and so forth. So, it is some sort of a broad measure of the zigzagging that has taken place. How much the function value has changed at the two ends. These are independent random variables. Now, the independent random variables, this is one property you know from the property of the symmetric random walk. Also you know the symmetric random walk, the expectation of the increments are 0 and the variance of the increments are the difference between the two time endpoints. Here actually one can prove through the central limit theorem that these increments actually follow normal distribution, which we do not prove because that would take too much of time. It is a very short and compact course. So, these are independent random variables and WTI plus 1 minus WTI, this random variable follows the normal distribution with mean 0 and variance Ti plus 1 minus Ti. So, if all these properties, two properties are followed, first that this has to be maintained whatever be the scenario, these in whatever be your time points increasing, if you take an increasing set of time points, finite set of time points, then these things are independent and these increments themselves follow normal distribution. For every I, of course, this has to be for every I. So, start from I equal to 0 to I equal to n, I equal to n minus 1 basically, I equal to 0 to. So, each of these is following a normal distribution. So, this is what is called Brownian motion. Does stock price follow Brownian motion? The stock price truly does not follow Brownian motion, though it looks like one, because Brownian motions can take negative values, because the symmetric random walks can also take negative values, but a stock price can never take negative values. Once the stock price is 0, that stock has to get out of the market, but it is a 0 value stock. So, stock prices are not really modeled using Brownian motion, but actually these stock prices actually were modeled by Bachelier in 1900, who was a student of Henry Poincaré, using Brownian motion, showing that the pricing of such commodities in the stock market of various instruments in the stock market can be achieved by solving the heat equation. So, he linked the processes in the financial markets to partial differential equations. And of course, his idea was lost and now later on he has become a very famous name. But the interesting part is that the way stock market or movements of stocks, stock prices are modeled, that is called a geometric Brownian motion, and then that is built using that will always give you a non-negative thing, which is built using a Brownian motion. And you can understand and take it as a trick that if you want to get non-negativity, always use the exponential function. So, that trick has been played in this area pretty often. So, now we will introduce what is called, if I want to define a filtration associated with a Brownian motion, how do I define a filtration associated with a Brownian motion? So, what I will do in this filtration associated with the Brownian motion. So, filtration, so this filtration Ft is a collection of sigma algebras this is a collection such that number 1, whenever t is strictly bigger than s, f of s must always be contained in ft, that you have more information as time evolves. So, this should always be contained in ft. Okay. Now, number 2 is that Wt must be adapted to the filtration. The Brownian motion must be adapted to the filtration. And the third point is so if you have this situation, then Wu minus Wt is independent of Ft, Ft. That is, once you move beyond t, Ft does not have any information about this. This is independent of what information you have in Ft. So, Ft basically collects, Ft can also be viewed in some sense as the smallest sigma algebra generated by the stochastic process till a given time. So, take all the values of the random variables omega t up to a given time and take the sigma algebra generated by them, that can be also viewed as one of the filtrations, right. You could have larger filtrations also, but that is essentially it is. So, once we know that we can have some filtration defined like this, we can prove that the Brownian motion is a martingale. So, again just do like this, take t less than equal to s. So, you will find that the tricks are almost similar. So, what I do is and now I break up the whole thing. You know, this is Ws is completely determined by Fs, it is known. So, you have to take out what is known. So, Ws is equal to Ws into 1, you take out the Ws, expectation of 1 of constant random variable is the same. So, now here Wd minus Ws as a third definition does not depend on Fs. So, it is nothing but it is, so there is no conditional expectation here. So, it is just the expectation. So, this random variable is just this constant random variable plus Ws. You take the WS out, expectation of 1 given Fs, expectation of 1 is 1 basically, that is all. Because 1 just a constant random variable does not depend on Fs, but this you know is 0 because of this fact. 0 plus Ws which is equal to Ws, and that proves that it is a martingale. There are several other martingales which are associated with the Brownian motion. A martingale that we are going to write now is very important in finance, specifically in calculation of risk neutral probabilities and all those things. So, this is a very important martingale called the exponential martingale. So, the exponential martingale is defined like this. So, exponential means this is e to the power. So, sigma Wt, where sigma is positive number, exponential means e to the power this. Of course, this itself is a random variable because you are taking exponential to the power of a random variable. So, it is now you are taking the exponential exponentiated by a random variable. So, this itself is a random variable. Now, the idea is that if you have a filtration associated with respect to Wt, then that same filtration will be associated with Zt. Because if Wt is adapted to a given filtration, Zt will also be adapted to the same filtration, because knowledge of Zt singularly depends on the knowledge of Wt, right. The question is whether it is a martingale. So, one has to prove that this is also a martingale. So, we start in the similar fashion. This proof is not as straightforward as this proof, though similar type of approaches would be used, but let us just go and do it. This omega, the sigma that you see, this we will finally talk about as volatility of the stock price movement. It captures how the randomness captures the massive movement of the it really gives you a feel of the zigzagging of the path, how the prices are, how fast they are going and coming down. So, that sort of, so this captures that idea basically. So, F is a filtration associated with the Brownian motion Wt. So, that is so, you have added sigma Ws and subtracted sigma Ws from here. Observe this, sigma square t is a non-random part, it is not a random variable, right. So, here is the product x into y. Okay. So, the question is, in these sort of situations, right, there are some deeper questions. If you go back to your original where we had written down the laws of conditional expectation, the rules, then we expected this and this product has to be integrable, because if you have to maintain the definition of conditional expectation. Of course, product has to be integrable means you need to define what is the meaning of integration of these two random variables. is such random variables are integrable? That is the question we are not going to answer right now. We will later on show that these are actually integrable. We will later on discuss the integrability of this, that is they are actually integrable random variables because they will come out to be solution of certain equations. So, and if you have a Brownian motion, how can you integrate it? Can you integrate it just like any other random variable? Can you find the expectation of a Brownian motion? The answer is yes, I can find the expectation of this Brownian motion because this is 0. Can you find the expectation of this Brownian motion? The answer is expectation of this Brownian motion is this minus half sigma square t. Now it will be left to the reader to decide whether, of course there are certain little technical issues I am not getting into, but it is clear that what is the meaning of integrability of a random variable? Integrability means that the expectation is finite. The expectation of this is finite, this is finite. So, this exponential function will have the integral, will be integrable, and this exponential function would be also integrable. So, at the end if you look at this part, so this is nothing but this part, but this part this is because this has mean minus half sigma square t because this mean is 0 and this exponential is nothing but a constant thing. So, mean of this is nothing but minus half sigma square t. So, this is a thing with finite mean. Now, if you take you are taking exponentiation, so basically you are taking expectation of the exponential function. If the random variable itself has a finite mean, then if you take the exponential function, that exponential function will also have a finite mean, it will have a finite expectation. That is why it is meaningful to apply the fact that I can take out what is known. You see, this part is known to me when at time s this whole part is known to me because this only depends, this is just the evolution of w, the random variable up to the time s. So, I will take this part out, taking out what is known, I will have exponential. So, it is very important to get certain technicalities cleared before you move, that you are actually applying the results correctly. That is an important thing that one needs to learn as one goes on doing more mathematics. Sometimes we can do some hand waving, but not always. Now, once I have this, remember that this thing is independent of Fs, which means I just need to calculate this. Now, what is this? Sorry, I will not have the Fs here, sorry, it is independent. Now, if those who know some probability, they will understand that I know that Wt minus Ws is a normal distribution with mean 0 and variance t minus s, and this is nothing but the moment generating function of a normal distribution. I have not spoken about moment generating function in this discussion, but if you forget about this term moment generating function, you can directly compute this expectation. I am not going to compute for you, this will come as a homework and this will appear in your assignments. So, what I am just writing down the answer, you can, this is a simple integration. So, I am just not going to do that. This is equal to exponential of half sigma square t minus s. Okay. So, this is what you will have, that is the answer. So, once you write that down, then the final answer would be the following, that if you write this as exponential, so you write this as exponential sigma w s minus half sigma square t, and then you write this as exponential half sigma square t minus s. So, this is nothing but exponential sigma w s minus half sigma square s. So, this is nothing but z s. There is another martingale which is helpful in finance, is the following, it is zt is w square minus t. So, this will also go as an exercise in a homework assignments to prove that this is a martingale. Now, we will talk about, so what is happening? We will talk about how to compute the joint probability of a Brownian motion at certain given time points. If you take Wt at any t, what is the distribution of this random variable? Wt can be always written as Wt minus W0, and this has normal 0t. So, if you want to know whether at a given time t your Wt is lying between some points A and B, it is obvious, you can just use the basic idea, that is the question is, suppose I have now n time points which are greater than 0, 0 I know where it is. So, you have these n time points and we ask you the question how to find, sorry, say Wt1 how do I do it? So, let me look at the case at the very first. This is how you compute what are called the transition probability densities. Let us see. So, now suppose you are given the information that under the given scenario Wt1, under the given scenario omega, Wt1 omega was x. Okay. So, suppose I know that it is known to me that at t1 for the given scenario W at time t1 it was x, where say x1 lying between b1 and a1. So, what I now want to do is I want to calculate the probability that Wt2 lies between a2 and b2 given that Wt1 is x1. That is what I want to do. But if you see, if I have fixed Wt1 as x1, then what do I have? I have Wt2 minus x1 as my random variable. x1 is known to me, that at time t1 x1 is what happened. So, now what is the probability that Wt2 would lie between the value of Wt2 for the given scenario omega will lie between A2 and B2. So, for the scenario omega at t1 I know what has happened, it was at x1. Now find, so it is on the state x1, so what is the probability that the next state would lie between A2 and B2? It is like sort of a transition, computing transition probabilities. So here if you look at this thing, the expectation of this is also a normal random variable, so this also follows normal random variable, but the expectation of this is what? Expectation is, so it is a, see here we had a normal random, so we had, so this new random variable z, so WT2, so is equal to z plus x1. So under this given information, the expectation of WT2, so WT2 under this information follows normal x1 with, because this is the time t1, so this z follows normal 0 at time t2 t1. So WT2 is nothing but x1 plus z, so WT2 follows this one, because this expectation is 0. So once you know this fact, then what would happen? This means now I can compute, sorry, I should be having, so we will apply the same idea of conditional probability, that probability of A intersection B is probability of A into probability of B, conditional, the way we write, sorry I am just, so probability of A given B is probability of A intersection B by probability of B, this is what we had learned. So we can always write probability of A intersection B is probability of A given B into probability of B, that is exactly what we are going to do here. So first we are computing the conditional expectation, and then using this we will write the joint probability. So this conditional expectation is 1 by, a conditional probability is 1 by x2 is the variable that I am using for the variable x2, x1 is what is the mean, dx2. Now if I want to write the joint probability, so this is my conditional density, this is my conditional density function, and thus I can write the conditional density function in a more simpler way. So I can write the conditional density function in a compact form, but let us do the general form and then we will tell you how to write the conditional density function. If you look at this, now I am writing this one. This is a joint probability. Okay, and this is equal to, so first I write the, I'll tell you what is the meaning of this. So these are the marginal probabilities, marginal densities. So the marginal density in general is given like this. So what is the density function associated with the fact my current state is y, and then in time t I will move to the state x, at time 0, say if my current state at time 0 is y, in time t I will move to the state x, what is the density function associated with that particular transition. So, this is called the transitional density function, transition density. What are the conditional density? Transition density, and that is given as 1 by root 2 pi t e to the power minus x minus y whole square by 2 t. Oh sorry, dt is not. So, this is my conditional density function. So, I would keep it as a exercise for you to write down for the case till n. How can you write it? So, here you see from 0 my state was 0, it is always 0, w 0 is 0. I have come to the state x1 at t1. Given that I am in state x1 at t1, within the time t1 to t2, I have within the time span t2 minus t1, I have come to the state x2. So, essentially a Markov process. Brownian motion is also a Markov process, those who knows about Markov processes. So, we are just trying to compute them by, this is nothing but a conditional, this is a transition probability actually. It tells you given the state is at x1, what is the probability that the state is between A2 and B2. So, next state. So, because it is a continuous thing, you cannot say that probability WT2 is x2 because that will become 0. So, you just have to say what is in between. So, that is the whole thing. So, I know what is at 0, I will come to the state x1. So, the conditional density at x1, this is the conditional density at x2. So, I am at time t1, I am at x1, and at time t2, so within the time span t2 minus t1 I have come to x2, then what is the conditional density? So, the joint integration of this would give me the conditional probability which can be motivated, which is motivated from this very basic idea. Thank you very much.